Hello, I'm Paul Fletcher. I'm the Bernard Wolfe Professor of Health Neuroscience at Cambridge University, and I'm pleased to be speaking to Dr. Heidi Johansen-Berg, who is a Reader in Clinical Neurology and Wellcome Trust Fellow at the University of Oxford. Heidi. Now, when I was training, there was a sense that the structure of the brain, once it was laid down, wasn't going to change, and yet the data you've been showing at this meeting and publishing over the last few years suggests that that's not the case. Could you tell us a bit about that, please?
Sure. So, in the past few years, there have been imaging studies done that have suggested that the gross structure of the grey matter of the brain can change with experience when people learn a new skill, such as juggling, for example. And what we've been particularly interested in looking at is whether similar types of change might happen in the white matter, the connecting fibre pathways of the brain. And the results we've presented here suggest that when people, healthy adult subjects, learn a skill such as juggling, the fibre pathways of their brain change over a period of weeks to months. The big question now is what that change means, what's going on in their brains to give us that change on our imaging measure. And we think that things such as changes in the amount of myelin wrapping around the axons, or even changes in the density of axons within a bundle, might be driving the effects that we see in our imaging data.
But how does one measure these changes? What techniques are you using over and above the standard MRI techniques?
So the technique we've been using is diffusion MRI. So in diffusion so it's using the same MRI scanner, but we sensitize our signal to the self-diffusion of water in the brain, which is a useful thing to do in this context because we know that in tissue with a highly directional structure such as a fibre bundle, there will be directional dependence to the diffusion signal, so we see more diffusion along an axon than across an axon. So by measuring water diffusion in this way, we can gain a number of important measures which tell us something about the structure of the tissue. So the particular measure we've been looking at is something called fractional anisotropy, which quantifies that directional dependence in the signal, and it turns out that that relates to certain biologically meaningful features of the bundle, such as the amount of myelin or the integrity of the membrane or the axon diameter or the packing density. All of those anatomical features influence that imaging measure.
And what implications would those structural changes in the white matter, you think, have for the way in which somebody carries out a task like juggling or some other motor task?
I mean, what the results are suggesting to us is that these kinds of intensive training regimes that we assume would result in intense and repetitive firing along specific patterns of axons in the brain, that type of intensive neuronal activity will have a knock-on effect on the structure of the brain. So we think that type of training regime will influence the brain structure in a way that might then persist for weeks or months.
So could one encapsulate it by suggesting that these changes make the system more efficient at that particular task?
Yes, absolutely. So the tie-in between structure and function is that we think that if you change the anatomical structure of the pathway, that will influence the efficiency with which information can be transferred along the pathway. So the probability of a signal getting from area A to area B will depend on the structural state of the pathway between the two regions.
Right. Well, Heidi, thank you very much indeed.